All right, now, yep. So this is my reminder that you should mark yourselves in the attendance list if you are one of the students who are officially registered to the seminar courses, either 579 or that other one, 7 something. You go to 579's Moodle page and mark yourself in the attendance. Otherwise, nobody knows that you attended. All right. So now here is, okay, consider yourselves warned about this. Here is what I mean. Okay. Now, computation, as we are familiar, I mean, being people in this department, we know that computation is about receiving some sort of input information from the outside world, then processing it in a certain way, like according to a particular transition diagram, particular program, I guess. And then, as a result of what you did, you produce an output. Okay, that's the picture that I draw in the first lecture of my automata theory course, for instance. That's what computation is. Some input is processed by some mechanism, and hopefully we get the output that we want, which is in some way correlated, which is in some way relevant, which is in some way like the correct answer to the question which was supposed to be written in the input. And the details, I mean, how the processing is done, I mean, exactly how the input is given and so on, are in a certain sense, I mean, if you are looking at it in a certain level, the details are not important. And what do we mean by not important? Well, we mean that, I mean, it can be implemented, this whole transformation from the input to the output according to a certain specification, certain function, can be done in lots of different ways. And we really don't care in theoretical computer science about exactly in which kind of hardware it is accomplished. All right? Okay, so usually we do it using our electronic computers nowadays, or like before the invention of electronic computers, I mean, all of us have those brains in our heads, and they run according to some electrochemical principles. But everybody knows that it could also have been done using some sort of hardware which is completely different than those, right? It can be done. I mean, we do it really in primary school or something on pen and paper, right? Or with little pieces of beads or stones or things like that. All right. So there is this level. Okay. The software level is sort of okay to work with any other different kinds of hardware levels and so on. Okay. So that everybody knows about computation. Now, what do we have in particular about unconventional computation? What does unconventional computation mean? Well, it is the study of the exploration of all kinds of different and usually unusual, usually like funny, okay, approaches to building computers. And usually they, as the examples will show, explore strange implications of the laws of physics. They play with you know, the basic assumptions that Alan Turing had while he was designing the Turing machine, the basic theoretical model of computation. I mean, what if the laws of physics were not like that? Then how would the computation work? They ask interesting questions like this. And they consider outlandish different ways of implementing computers. Some examples will make what I'm trying to say here clearer. All right. So if you look at this, if you like force yourself to change some things that you have already you are maybe assuming that are essential for computation, all right? then it makes you understand this whole idea of what is computation and how it can be done in a better way. All right, and usually considering those things is fun as uh, as a motivating factor. So let's go ahead. Now, there are really many different ways of thinking about what computers could do if we used some of the interesting results that that have been discovered by people like Albert Einstein or the guys who developed quantum theory, quantum mechanics in the beginning of the 20th century. And what if we applied those strange but correct ideas, those strange facts about nature to our models of computation? One of those ideas is the concept of relativistic computation. Now, you have heard about Albert Einstein's. You have heard of somebody called Albert Einstein, right? And he was this great physicist who made like revolutionary contributions to physics in the beginning of the 20th century. And among other things, one of the things that he discovered, I mean, and those things have been verified again and again, some of them like decades after Einstein's death, and so like pretty much what he theoretically discovered turns out to be correct, is that okay, time doesn't pass at the same speed for everybody in the universe. It depends on how fast you are going or in what kind of place you are sitting at. Two people who are like sitting at different places may experience time flowing at different speeds. All right, that's I mean, most of you, I'm sure you have heard about it, but this is like, this is not science fiction. This is absolutely correct. And the operation of those satellites which communicate with your phone and tell you where you are in Google Maps and so on, they depend on this kind of physics. All right, so in particular, a pretty simple conclusion of Einstein's results is that if you are in a location with a stronger gravitational field, like where gravity is stronger, time passes more slowly for you than somebody who is sitting, existing in a location where the gravitational field is not so strong. And what does this mean, really? I mean, for instance, if you are nearer to the surface of the Earth, right? I mean, if you are at sea level, if you are in Istanbul, okay, and compare yourself with your twin in a very high place, like on top of Ağrı or whatever, right? Now, because of the difference between the two of you to the center of the Earth, the gravitational field is somewhat stronger here in the lower level in Istanbul, right? And for this reason, you will age more slowly than your twin, who is like up there in orbit or at the top of the mountain. Correct, right? I mean, they have measured it for those two American astronauts. Remember the twin astronauts? One of them spent a lot of time around the Earth, and the other one was sitting on the planet. This happens, all right? So, in what way does this help us for computation? The people asked this kind of thing. That's the kind of questions that those people ask. Okay, so you know that there are some famous computational problems for which we are not able to find fast algorithms. All right, I mean, you have heard of NP complete problems. We strongly think, although we have not been able to prove yet, we strongly think that NP complete problems don't have fast algorithms in the sense of computational complexity. So if I ask you a question belonging to that sort of category of sufficient size, I mean, it may not be possible for you to run the best program in the world and still get an answer earlier than 1 million years, right? What if you really want to obtain an answer to that kind of question? Okay, typical sort of problem for an unconventional computation person. All right, and I have actually listened to seminars and read serious scientific papers about that kind of thing. So basically, the idea is as follows: you prepare your program, which is supposed to run for, I don't know, 1 million years, and then later it will print out the answer, and you really want to know what the answer is. All right, so you go to a black hole, or a place where the gravitational field is really, really, really strong. All right, you go very near the black hole, where like the time passes really, really slowly compared to other places in the universe. But you don't take your computer with you, right? You leave your computer away in the area with the low gravitational field, and you yourself go very much near the black hole without being consumed by it, right? Where time goes slowly for you, and you send a signal to your computer and it starts running. Now, what happens? Although the computer takes 1 million years according to its own clock while it is running, you only age a few hours, right? Or a few days, okay? And at the end, the computer finds the solution, the answer to the particular question, and sends it to you, and you are happy because you now know what the answer is. That's one way of applying strange physics to solve an otherwise very difficult computational problem, right? Of course, there is a issue here. If you do this, then all your friends would be dead, right? Dead for 1 million years, all right? But still, it is a possibility. And people also have examined whether this kind of thing, I mean, whether by maybe entering the black hole itself or something like that. I have read certainly strange physics papers about this. Would it be able to beat the computability barriers? I mean, Alan Turing has proven that certain problems are, they don't just take very long on computers, they are like impossible to solve on computers. They require like infinite amount of time in order to see whether it has stopped or not, the program has terminated or not. Unfortunately, because of like big technical reasons having to do with quantum theory and so on, you don't have that advantage even if you like jump into the black hole. You still cannot solve the undecidable, unsolvable problems designated by Turing, even using these extremely extreme methods. All right, so that was one pretty simple example of unconventional computation. There are also other ways that physicists have examined computation. You may have heard about this one. What is the minimum energy requirement of computation? Because as computers get smaller and faster, we are reaching some physical barriers about what we can do and how much heat is generated during the computation process and so on. And this has been the subject of very serious examination by physicists and computer scientists who learn about physics in the last 50 years. And it turns out that quite surprisingly, if you are looking at this problem from a theoretical perspective, it is possible to do computation without using almost any energy. I mean, I'm not saying zero energy, but the physics results show that like give me like a non-zero number, but very, very small non-zero number, and I can design a computer system which requires only that much energy while working. All right. Now those sort of don't look like our present computer systems, but they are designed thinking about concepts of thermodynamical reversibility, the second law of thermodynamics, all right, things that you may have heard back a few years ago in some physics course. Essentially, they have to do with whether the processes that are executed by the computer while doing all those things are thermodynamically reversible or not. What do I mean by thermodynamically reversible? I mean, let's say that your computer is running, it's got this input, it computes, and it prints its output. Now, if it is possible to compute seeing the output, right, and the code of the program, what the input was, if it is to like go back from the output to the input by just knowing the code of the program, then we say that that program is a reversible program. It maps every different input string to a unique output string. Essentially, that's what it means. If you are careful and if you write your programs according to this principle, and people have shown that it's really possible to write your programs according to this principle, then yeah, indeed, you can reduce the energy costs, energy requirements of your computation down to any positive level that you are theoretically interested in. And people have taken this idea and have thought of many strange, interesting ways of building computers out of ideally reversible materials. And one of them, you may want to like look it up in Wikipedia, or there are some like wonderful resources for this topic. Richard Feynman's lectures on computation, for instance. But like the most famous one is the billiard ball computer. What do I mean by the billiard ball computer? Well, think of billiard balls, a pool table, that's the English word for it, right? I mean, you kick some balls, and the balls kick the other balls and some walls, and they enter some holes on the other side of the table or not. Well, you may represent a computation using this kind of thing. I mean, the ball entered this hole means 1, the ball didn't enter this hole means 0, for instance. Or the ball passed through this location means 1, and it didn't pass through that location means 0. By interpretations like this, you really can build computers out of billiard balls and pool tables with artificially introduced balls in the middle of the table and so on. And assuming that the balls are working like ideal balls, like without friction and so on, they make really fun computers. There are exercises about this. There were examples about this in my lecture that many years ago. So essentially, this is how they implement an AND gate, one of the many implementations of an AND gate. Essentially, I mean, from the two locations at the top and left, you send two balls. If there are balls coming in from both locations, it means that both inputs to the AND gate are 1. If there is no ball coming in from a location, it means that that particular input is 0. And only if two balls come in, I mean, only if both of the two inputs are 1, they collide, and then one of them goes out of the AND out location, meaning like that's the implementation of an AND gate, right? Otherwise, no ball goes out of the output location, meaning, oh, the AND gate has resulted in 0, right? You can implement basic gates like this, and of course, if you can implement basic gates, then you can implement any computer, right? Using billiard balls. And nice thing about this, once again, I mean, why did people think of this crazy idea? Is that because it's reversible? Because, I mean, assuming that there is no friction and so on, assuming that those are ideal elastic balls, the whole thing can run backward as well. Think about it, right? It makes sense to run the entire thing backward according to our physical intuition. Anyway, let me talk about one other crazy application of this idea. Crab computers. You know what a crab is? Those animals that go sideways, right? So some people in Japan and England worked together to implement this billiard ball idea using swarms of crabs. Okay, what do I mean? I mean, think of thousands of crabs. It turns out that this particular species of crabs moves in swarms, like hundreds, thousands of them run on top of each other, and they move in a particular direction. So these Japanese researchers said, you know, if we organize a sort of labyrinth in which different corridors correspond to different Boolean variables, and whether a swarm of crabs, like 100 crabs on top of each other, is walking through a corridor means one of this variable, and no crabs are walking means zero in this computer, right? And if we just send several different swarms of crabs through several different corridors, when two swarms meet, they collide like what elastic balls would do in billiard balls, right? And they are trying to implement OR gates and AND gates and things like that by designing specially configured pyramids, and then sending swarms of crabs corresponding to different binary strings from those locations. And they are controlling the crabs by dropping a particular shadow of a bird on top of them, so that they think that the bird is about to eat them, and they start moving in a particular direction also. So crab computer. All right, I can send you the link if anybody is interested. So yep, okay. So and also, of course, we have quantum computers. One of the most famous ways of using strange physical things in order to do computation. And although quantum computers are nowadays becoming more and more commonplace, so maybe in later years I won't mention them in lectures about unconventional computation. But anyway, the basic weird thing about quantum physics, as most of you know, is that essentially, I'm simplifying everything down, but essentially these two things are enough. The same thing, the same object can be in two places at the same time, according to quantum physics. Now, you can see this only for very, very small objects under very, very special conditions, but physics says that it really is possible. Now, that's a very interesting thing. Same thing can be in two different places, two different states at the same time. Furthermore, these two copies of the same thing can then be made to cancel each other out in a certain configuration, right? I mean, one copy of the same thing, another copy of the same thing, but the sign of this one is the negative of the sign of this one, and whoop, they cancel each other out. They are gone. That's called interference in physics. Things like that can happen. And people have built quantum algorithms like Shor's algorithm, famous Shor's algorithm for factorization and so on, in order to make use of these strange things. And really those work, all right? This is really something that physicists say works. Not only that, it actually works in laboratories. Those people in Google made that chip which solved a very difficult problem that is difficult for classical computers, using this kind of thing. I mean, if you haven't heard of quantum computing before, I mean, please believe me, it works. Anyway, making use of those ideas, now I think I'll tell you a little bit about my work on this kind of strange thing. I, together with my ex-PhD student Abuzer Yakargınmaz and some other people from Latvia, we wrote a paper called Quantum Computation with Write-Only Memory. Now, write-only memory is a joke, right? I mean, it was a joke when we were young students, but thanks to this idea of different paths of different versions of the same object canceling each other out or reinforcing each other, we were able to actually develop a computational model where if you add a printer, if you add an output device to a quantum computer, you know, what's special about an output device? It's write only. I mean, once you have written it, you cannot use it back as memory, right? You cannot read it again, all right? But we showed that we developed a very nice model where you add a printer to a quantum computer and its computational power increases, right? It is able to solve certain problems that without the printer, it was not able to solve. You see what I mean? You have a computer, it has a certain computational power, you can prove that it cannot solve certain problems, right? But then you add a printer to it. The only thing that this new model is able to do is to like print certain things out, okay? And now this new system can solve those previously unsolvable problems because of that strange things that quantum theory says you can do on the printer, all right? We essentially made it print like different things on different quantum parallel worlds on the printer so that the wrong solutions canceled each other out and only the correct solutions survived. So when you observed the machine, you only were able to see the correct solution. Okay, crazy enough. If you think that this is not like weird enough, let me finish with another of our work. Time travel. Okay, I mean, sorry, but Albert Einstein's physics, the general relativity, which I was mentioning at the beginning of my talk, also allows the possibility that you can send an object back in time. Nobody has been able to do it, but the equations, when you like look at the equations carefully, and the first person who was able to realize that the equations really are saying this was the famous Kurt Gödel. You have heard of Gödel's incompleteness theorems, right? Einstein's well-known, well-respected equations, which we think are correct, tell us that it is not forbidden to send an object back in time. All right? Now, what happens when you send an object back in time? Of course, certain, you have heard of all those science fiction stories where somebody goes back in time and kills his own grandfather when the grandfather is a child. And, oh, but then since the grandfather is dead, the father doesn't get born, and then the time traveler doesn't get born. Isn't that a paradox? That well, there are mathematicians who say that we can go around this paradox by assuming that the universe makes the universe sort of makes a computation automatically when a time travel occurs, so that it sets itself in a superposition of possible worlds in which, when you look at it from the big perspective, no contradiction is happening. So like it makes the universe do some computation for you. And several computer scientists in the United States have asked this question. What happens if we send like a few bits, like 1 bit of information from the future to the past? If I have a computer which like takes an input and computes something and arrives at a result, but at the very end, it also produces a single bit of information, and it has the capability of sending this single bit of information back to the point in time where it was starting the computation, and it receives that bit that it itself sent from the future and uses it as part of its input. Now, if we have this capability, how would this increase our computational power? What kinds of problems would be more easily solvable if we had this capability of sending just one bit of information from the future to our own past and then processing it. So it's a sort of loop. It's a sort of corresponds to finding the stationary distribution of a Markov chain, if you are interested in like what's going on here. And it becomes even more interesting if you allow the computer doing this computation to be a quantum computer, and if you allow the bit that is being sent back in time to be a quantum bit. I mean, one of those things which can be both 0 and 1 at the same time, both here and there at the same time, all right? And it's an active area of research. Real people write real articles on real scientific journals about this. And we have also done that. So here are a few of our articles about this. With Abu Zer, we defined, we actually solved the problem about the computational power of what these machines can do. But we didn't, we weren't able to solve the question for quantum bits. We were able to answer the question though for classical bits, like normal bits, okay, which go back in time. And then a few years after that, some of you may have already met him, a great guy called Ryan O'Donnell from Carnegie Mellon, arrived at our department for a sabbatical. And I described to him the problem, and we started working on the quantum version of this problem. And we also said, you know, what if not one bit, but more than one bit is sent back? In what way does this affect the computational power? First of all, we were able to prove that 2 bits, 3 bits, 4 bits, as long as the number of bits being sent is only logarithmically bounded in terms of the length of the input to the problem, there is no difference between sending 1 bit or like 10 bits or something like that back in time from the computational power perspective. And then, I mean, most of the work here was done really by Ryan. He's a genius. He was also able to solve the same problem for quantum bits as well, all right? And if you are interested in that kind of thing, we were able to show that a computer augmented with that kind of time travel device solves exactly a particular, its computational power corresponds to exactly a particular pretty famous complexity class. All right, so this was a good characterization. Anyway, so we are living in the days of Corona and everything is crazy. So that was a crazy presentation for you. Thank you very much for listening. If you have any questions, please raise your hands using this Zoom thing. I will see your hands. If there are no hands, then, oh, somebody raises a hand. Okay. Now, Arda, I see your hand. Now I'm trying to, yeah, I am, okay, you have unmuted yourself. Go ahead.
Yeah, thank you. Thank you very much for your presentation. I just ask one question. So you're talking about time travel and sending 1 bit back in time. Yeah. But isn't that easier? We can, for example, run the machine and look forward in time and see the result of it and retrieve it and use it. I think it's more theoretically possible than sending a bit back in time.
Well, seeing the future corresponds to, I think, calculating the future, right? I mean, if you are able to do some, I mean, what do we really mean by this person is able to see the future very well? He's got a big computer in his head, and he's able to do better computations than us, right? So that again would be a complexity theoretic problem. That would be a good model in itself. So I invite you to work on it.
Okay, thank you.
Thank you for the question.
By the way, regarding the same topics here, recently I watched a TV series called Devs. Anyone interested in these kind of quantum things, I suggest you people to watch it.
Thank you very much. Arda is very good in that kind of thing. Please share with us the details. Yeah.
Okay, thank you.
Okay, thanks. So, Any other questions? Okay, yeah, Hatice Esra Aydemir. Yes. Yep.
I want to ask how is the write-only machine works with the printer? I couldn't get the difference. Does it already compute it, but just gets the option to print, or what changed?
Yeah. Just think of it as exactly a printer, all right? And the interesting thing about quantum is that there are those multiple parallel worlds, right? And so in our setup, the machine, when it is about to make the wrong solution, right? It divides itself into many parallel worlds. There are actually many parallel copies of the machine, and we were able to make it so that the versions which printed wrong solutions on the printer, right? The parallel worlds which were printing wrong solutions, wrong solution number 1 and wrong solution number 2 to the printer, they were able to cancel themselves. They canceled each other, and what remained was only the versions which calculated and printed the correct solution. Okay? If you wish, I can share with you the paper on that. Right? I'm quite
I'll be
proud,
happy.
quite proud of that paper. I don't know if anybody will use it, but to actually be able to use write-only memory, something we were joking for like 35 years with my classmates, was a very fun idea. Okay,
Thank you.
Thank you very much. Okay, everybody, thank you very much for listening, and have a healthy time. Bye-bye.